All right, we got about 3 more minutes. I'm not seeing any questions in the text channel of today's date. So if you have any questions you want to ask, you can either use the text channel, you can voice chat, or you can send me a direct message if that is what you want to do. But it's a good idea to ask questions, make use of this time before class starts. All right. And I will talk about the co-requisite prerequisite thing that was mentioned in the announcement. So we'll talk about it in class. So I'm gonna wait until everybody is here before I get to talk about that. All right, we got 2 more minutes. And I also got a question about set representation, using integers and bitwise operators. So I can talk about that a little bit today too. So if I get to that point and not forget to talk about it, you guys can remind me to talk about it. All right, I'm hearing a whole bunch of popping sounds. That's probably from Yolanda. Thank you. Cool. And just as a geeky thing, I got of all things, I got a sound blaster. Okay, which is a kind of old thing. If you ask your parents, they would know about sound blaster. So I got a sound blaster USB dongle thingy. It's a version 3, $20 from Amazon. And you guys may say, but why did you get something like that? Don't your computer already has an audio port? The answer is yes, my computer does have an audio port, but that audio port or the chipset doesn't have a feature for mic monitoring. In other words, I cannot hear my own voice, through the mic, back into my headphones, and it's not it just feels kind of really strange, okay? Because I have a relatively good it has good isolation. So when I cannot hear my voice, using the external feedback, it just kind of feels weird, and I have to look at the audio mixer, just to make sure that I'm not speaking too softly or too loudly. And having that feature turned on, which I can do now with this USB dongle, makes it possible that I can actually listen to my own voice. All right, so we got 5 more seconds to go, and I think the streaming is on already. So for people who want to watch it through YouTube, that part is on too. All right, it's time to get started. So the first thing I want to do is to mention that in this class, if you go all the way to course information in Canvas, I added 2 quote-unquote assignments. They're not really assignments, they're just a way for me to track prerequisite and also co-requisite requirements. So one is for the math prerequisite, and the other one is for the CISP440 co-requisite. There's no entry here to check CISP 360, because anyone who has met the CISP 430 co-requisite would have automatically met the requirement of CISP 360. So let me just kind of go to one of these and show you what it looks like. And I can go here and use a student view. So this way you get to see what you should be seeing and not what I should be seeing. So in this case, you can go to submit assignment, and it allows you to upload a file. I believe you can upload more than one file, so I'm not 100% sure. You can also have a text entry, okay, which is just the HTML editor, to add your own comment if you want to. There are other options too. Google Drive, I suppose, this allows you to include a link. Oh, okay, this tool is not available because I am masquerading. But basically, I just need a if you have a point of 1 already, if you check your quote-unquote grade for this one and you already have 1 point, that means you're done. Okay, I have checked and you have met this particular requirement. If you checked and you either get a 0 or it is blank, that means you have not met this requirement. And some of you are going to go, but I took I took Math 370, and it doesn't show up on my professor's prerequisite list. Well, that's okay. All you have to do is to get a unofficial transcript. Go to eSurfaces, get back to the grade, of your Math 370. Make sure whatever screen capture or PDF document you're going to send, has your name and also which college you took Math 370 from, and also your grade, which needs to be at least a C or better, and attach that to file upload. Okay. At least one of you, sent me a screenshot through Discord. That does not count. Okay, so you have to send it through this way, because I'm going to, by February 11th, I'm going to go through all of these. I'll check, everything that gets uploaded, and that is how I'm going to clear the requirements. So do not use any other means to send me the documents. Okay, not email, not Discord. Okay, you have to do it using this assignment. Okay, that is how you turn in the document. Alright, so I'm just checking the text channel. There are no comments, no questions. Alright, so the math thing is not too big of a deal for most people, because most people have taken, I just checked, okay, most people have taken at least Calc 1, some have taken Calc 2 already. So most people have met this requirement already, so no big deal. CISP430 is a bigger one. Okay, there are only a few people who have taken CISP430 according to the prerequisite check. So the majority of this class will need to send me a proof that you are currently enrolled in a section of CISP430. It doesn't have to be from ARC, it can be somewhere from within those reels, or if you're taking this class from another college district, then you will also let me know that and send me proof that you are taking this class from somewhere else. Alright, so I got some comments in the text channel. If there is no grade, does that mean I need to send a confirmation? Yes, I believe that is what I said. Okay. So these need to be done by February 11th, because the last day that I can add people is the next day. So I'm gonna have to make room, in the class, and I will basically just do one last batch of late add if I need to at that point. Alright, so I think there are no further questions about this, and if you do have any questions about this later on, you'll just go ahead and send me an email. And somebody was using the the text channel from last Wednesday. Okay, so let's use the one from today instead of the previous one, because we are now using the one from today. I do not know. So the question is, what is the possibility, or what are the chances, I suppose, of getting into CISP430? I do not know, because I'm not teaching that class. So you might want to check with the professors who are currently teaching that class within the district. Okay, so I believe we have at least one section, and some of the other colleges may have some sections as well. But the prerequisite and co-requisite requirements are listed even on the schedule. So next time, when people sign up for classes, I would advise reading those requirements carefully, so that you don't run into a problem of, but I signed up for the class, but I haven't met the requirements yet. It's best to check those things first. Okay. Alright. So enough of the bookkeeping kind of stuff, and we are now moving back into the class content. Last week we were done with Boolean operators, and today we're gonna, we are already in basic set theory, so we are just continuing on that topic today. So that module is right here, and I'm hoping all of you had a chance to read this entire module, which was an a recommendation from last Wednesday. So I'm going to make that assumption that you have already read this entire module. So this way we can breeze through the text and I can show some examples so that you guys can get a better understanding of the material. So here is section 2.1, and at least one student, okay, I cannot count how many have asked, but at least one student had asked about this one here: how do we implement the concept of a set in C or C++ or Java or some other programming languages? And the reason why this is useful is because a lot of algorithms are based on, they utilize the concept of a set, okay? But a set, unlike an array, is not a built-in construct in most programming languages. So now the question is, how do we get it implemented? I would like to kind of get into this topic a little bit. Not a whole lot, just a little bit, because someone asked me specifically bitwise operators. Okay, there were a few text questions and answers from the previous class from last Wednesday. So I'm just going to expand on that a little bit, and I can use my tablet to show you how bitwise operators work. Okay, there we go. So now we got the tablet on, and we'll go ahead and go through a few examples. So we'll start with I'm just picking a number, okay? Let's say 23, okay? And we'll pick another number. Let's say, I don't know. I got to pick one that's going to work, so I cannot just randomly pick another number. Let's say 51, okay? So this is going to work. So 23 is a base 10 number, okay? And 51 is also a base 10 number. So the way the bitwise operators work is we first have to look at the values in base 2. Okay, so we have to look at 23 as a base 2 number, and then we have to look at 51 as a base 2 number. If you have not taken a class where you were taught how to do base conversion, I'm not going to talk about it here. Okay, but this is a way to implement a set. It's not the only way, so just one of many ways to do it. So with 23, it has a so the way you do this is the easiest way to do it, okay, is to write down powers of 2. So 1, 2, 4, 8, 16, 32, 64, and so on. But we know that the 64 is not even needed because of these two numbers. The larger one is 51, so it's less than 64. That means the 2 to the power of 6 is not even needed. So for both values, they do not have any 64s, and for one it has a 32, the other one does not. Oops, the other way around. So for 23 it does not have a 32, but for 51 there is one 32, and then for the 23 there is a 16, and then for the 51 there is a 16 as well as a 32. So that will take care of 48 out of the 51. And for the 23, once we take care of the 16, we have a 7 left. And 7 has 1, 4, 1, 2, and 1, 1. And then for the 51, once we take care of 48, it has 3 left, which has no 8, no 4, 1, 2, and 1, 1. Okay, so this is how you can kind of visually convert a value into its base 2 or binary representation. So now we're going to work with these two and go like, okay, what do you mean by a bitwise operator? Okay, so I'll just give you some examples. So we'll go ahead and look at 0, 0, 1, 0, 1, 1, 1 in base 2. And this time we'll do a bitwise AND with 0, 1, 1, 0, 0, 1, 1. Okay. So as the name implies, a bitwise AND operation is performing an AND operation for every bit position. Okay, so bit 0 is going to be ANDed with bit 0. Okay, so bit 0 of the first number is going to be ANDed with bit 0 of the second number. Bit 2 is going to be ANDed with bit 2, and so on. So now we have bit 0 ANDed with bit 0. So 1 and 1 is a 1, 1 and 1 is a 1, 1 and 0 is a 0, 0 and 0 is a 0, 1 and 1 is a 1, 0 and 1 is a 0, 0 and 0 is a 0. So this is the bitwise AND result of those two values. What about bitwise OR? Kind of the same idea, except we're using OR instead of AND. Okay. So this time we have a bitwise OR, which is a vertical bar. 1 or 1 is a 1, 1 or 1 is a 1, 1 or 0 is a 1, 0 or 0 is a 0, 1 or 1 is a 1, 0 or 1 is a 1, 0 or 0 is a 0. So this is the result of bitwise OR of those two particular values. Now, how do you test all of this, right? I mean, is there a quick way to test this? Well, as it turns out, there are very quick ways to test this sort of thing. I'm just trying to get to a command line interface that has a relatively large font, which is this one here. You can always do this, in some other way, but I'm lazy. I just use GDB. So when you're in GDB, you can always just say print and then give it an expression. As long as the expression is not trying to refer to any variable in a program, it's gonna work. Oh, tablet in the way. Thank you. I haven't programmed a way to get rid of the tablet at this point, so I'll get to that at some point. All right, so we can do a print /t. Okay, this is going to print something in binary, and then we'll say 23, and you can see 23 is 10111. The leading zeros are not printed. It's only it will start to print the first non-zero from the left-hand side. And then the other one is 51, and it's 110011, and that means the way I did the conversion is correct. Okay, if you go back to the tablet screen, that's exactly what I did, what I got. And now you can say, what about 23 bitwise AND, which is a single ampersand with 51, and it gives you 10011, which is what we got. And then you can also change the bitwise operator to an OR, and we're gonna have 111, which is also what we got on the tablet. So this is how bitwise operators work. So what about the bitwise operators? How does that have anything to do with implementation of a set in C and C++? So if you are working with a set where the values that you need to contain in a set are all unsigned integers, and they go from 0 to 31 or 0 to 63, then what you can do is use one bit of an integer to represent the presence or the absence of a particular integer. Okay, so if I were to go back to my example, okay, let me switch to my tablet. Yeah, a hotkey would be very helpful now. So if I go back to here, okay, and I'll just kind of focus on 23. So 23 is basically saying this is equivalent to saying 0 is present, 1 is present, 2 is present, 3 is absent, and 4 is present. And then the other one would basically be saying 0 is here, 1 is here, 2 is not here, 3 is not here, 4 is here, and then 5 is here. And they go like, what are we talking about? Well, that's because this is bit 0, this is bit 1, bit 2, bit 3, bit 4, bit 5, and bit 6, and so on. So each bit, okay, is basically indicating the value of a bit is indicating the presence or the absence of the integer, which is corresponding to the position of the bit, whether it is in the set or not. Okay, so that is a very quick and efficient way of representing a set. But it does have a limitation, because all we can represent in this case would be from 0 to 31 if we're dealing with a 32-bit integer, and from 0 to 63 if we're dealing with a 64-bit integer. You can always extend it. You can always use an array of chars, an array of ints, or whatever. So that way you basically look at the concatenation of all of those constructs as a long bit pattern. Then you can, we can actually represent, a set that can potentially, have values up to however you want. But it is not very efficient when you have a sparsely populated set. In other words, if you have a set where values that you want to contain can go all the way up to 1023, then you're dealing with 1024 bits. Okay, if most of the time you only have one or two elements in the set, it is still okay, it will still work. It's just not very efficient. Okay, so not the most efficient way of representing a set, depending on the density of a set. Okay, how many items are usually in the set. All right, so I'm gonna hide the tablet again. Okay, are there any questions about bitwise operations? Bitwise AND, bitwise OR. Oh, I'm gonna give you bitwise, the bit shift operator too. So bit shift is really kind of helpful because when you have a bit shift to the left, that means a is a binary bit pattern and it's going to be shifted to the left hand side by b many bits. Okay, so I'll give you an example. Okay, we'll take a look at 3 left shift by 4. Okay, what is that? Okay, so we look at 3. 3 is 1 1 in base 2. So we are shifting 1 1 in base 2 4 times to the left hand side. Every time we shift by one position, we're filling in from the right hand side with a 0. So that means this is the same as 1 1 in base 2 shifted by 4 times, which is then 1 1 and then followed by 4 zeros, 1 2 3 4, but this is all in base 2, and that is representing 3. It's the same thing as 3 times 16, which is 48 in base 10, because we have 3 of 16s. That's one way to look at it. All right, so any questions about bitwise operators and how it relates to the implementation of set? Okay, all right, so if you don't have any questions, it's okay. I'm not expecting too many questions until we get to set operations. Section 3. Okay, so we are now moving on to section 3, and section 3 talks about how do we know that we have two sets and they are equivalent, they equal each other. Okay, so that is actually a very tricky topic because a set can contain another set. Yep, so that can be a little confusing. Oh, the tablet is in the way too. Okay, let me turn that off. There we go. So we are now in section 3. We are talking about how how do we compare, how do we look for equality between two sets. So we'll go through a few examples. So I'm going to turn the tablet back on. So these are examples that are not in the notes. Okay, so if you think these are important, you might want to kind of track these things. You'll use your own way of organizing the notes. So we're going to take a look at some examples. And we'll say, x equals to, so we'll try something simple first. Okay, x is a set that has 1 as an element. Y is a set that also has 1 as an element. Okay, you go like, okay, that's pretty easy because x equals to y is true. Okay, because these two sets are equivalent. Okay, if you give me set x, or if you give me set y, they will work equally. They're interchangeable. Okay, so now we look at another example. So this is one example. We look at another one. So this time x has element 1 and element 2. Y has element 2 and element 1. You know what? This time they are still equal. They're exactly the same. This has to do with something that we talked about last Wednesday, that the order of how things are listed in a set is irrelevant. Okay, there's no inherent ordering of items in a set. So whether I list 1 and then 2 or I list 2 and then 1 doesn't make a difference. Okay, all I need to know is it in the set, not the position is irrelevant. So do we have any questions about this particular example? Why the set of 1 2 is the same as the set of 2 1? Okay, all right, no questions. So now we look at something a little bit awkward. Okay, x is called the empty set. In this case, it has no element, And then y is also the empty set. Okay, is an empty set equaling to an empty set? The answer is yes. Okay, they are equivalent. They're interchangeable. Okay, instead of using x, I could use y. So in this case, x equals to y is also true. All right. So now we think about things like, what if we have a set that also has a set in it? Okay. So now we have x represented like this, and then we have y represented like this. Okay. Now this is where you really have to get rid of all the C ideas in your head, because in C and C++, okay, if you use like 5 consecutive open curly braces and then close a section of code with 5 consecutive closed curly braces, it's the same thing as using 1. Okay. But in this case, it's not, because in this case, x only has one element in it. So let me say that one more time. X only has one element, but y has 2 elements. Then you guys go like, yeah, we can really see why y has 2 elements, because it has 1 as an element, it has 2 also as an element. But how come x only has one element? Because x only has one element, that element is a set itself. And that element of x has 1 as its own element, and it also has 2 as its own element. So in this case, x equals y would be false. Okay? Do we have any questions about this? Because this is where things get a little bit strange. Okay, alright, so we don't have any questions. Alright, so if we get into questions, we'll deal with that, okay, at that point. And obviously, if we can have a set of a set, that means we can have a set that has an empty set in it, and then we can also have just an empty set, just like the other one. X equals to y is also false in this case, because x itself is not an empty set. X itself is a set that has one element in it. That element is an empty set. Y, on the other hand, is an empty set. There's nothing in y. So I got some people asking questions in the text channel. I'm gonna wait a little bit before we move on. In the 4th example, no. Nope. X is exactly the way I put it. It's not in the way that is displayed in the text channel. So the way it's displayed in the text channel, there are 2 different sets, right? One set has a 1 in it, one set has a 2 in it. I have no idea how those 2 sets are related, but there are 2 sets. Okay, so I'm not sure whether that point is clear or not. Okay, so got several people typing. Alright, so we got one question. So what if x equals to 1? Okay, the first thing is, if we do not use the curly braces, it is not a set. So the way it's typed in the text channel without the curly braces, neither x nor y is a set. So, but we do have, okay, so I'm going to write it in the tablet here. So I'm going to assume that x is a set that has 2, 1 in it. Y is a set that has 3, 4 in it. X equals y would be false. Because the way it works, the way a set is equivalent to another set, is everything in one is found in the other one, and vice versa. That is one kind of quick and easy way to define equivalency of a set is if you find something in one, you have to find it in the other one too, and then the reverse has to be true. What has to be one basically? Oh, it has to be 1 to 1. Sort of. Okay, and then one more. No. So the other example of X being a set that has a set of 1 in it, and Y being a set with just 1 in it, the equivalency would be false. They are not the same. Because one has 1 as a numerical value, the other one has a set. I don't even care what is in the set in X. X has 1 element, which is a set. I don't even care what is in that set, because Y has a value in the set. X has a smaller set in it. So, they are not equivalent. In other words, the set of 1 does not equal to 1. Okay, great. And then we got one more text coming. No, they would not be the same, because the set of 2 and the set of a set containing 2 and the set containing 3 would not be the same. All right. Because if you are, so it's a recursive type of comparison. You kind of have to drill down to the actual value at some point. So if the value once you drill down all the way to the actual value and the values are not the same, then we have inequality. All right. So we're moving on to, what I just said is actually a little bit ahead of time. That's actually what we need to talk about in section 4. A set can be an element of another set. Okay. But otherwise, so it's good to go through one of these examples. In general, given two values x and y, knowing that x is a set, this is how we can determine whether x equals to y is true or not. Oh, right, I keep forgetting that. Because on my screen, it is not on top of it. On my screen, it is actually somewhere else. So I need a way so that what I see is what you see. That is kind of important. I suppose that can be arranged. I remember why I didn't do it that way. Because if I did it that way, it doesn't do dithering. In other words, some of the fine lines would disappear because those are single pixel lines. But if I do it the way that I am currently doing, the fine lines would actually appear as lines too. So there's a reason why I do not use the tablet screen on top of my actual screen, so that it's easier for me to see whether the tablet is on top or not. Anyway, okay, so we're gonna go through the description here. So this is how we determine whether x equals to y is true or not. So we already know x is a set. If y is not a set, then x equals y is false, because the types are not the same. If y is also a set, then we use a recursive definition. We basically just say, okay, for each element in x, okay, does that element, can we find that element in y? Okay, and we basically go back to section 3 to do the basic, the basic comparison. So, okay, so we can take a little pause here. In fact, we can look at the next example and then we'll pause. So this example here is basically saying, okay, let's define x to be a set of 3 elements. So how come x only has 3 elements? It has A as an element, it has B as an element, and then it has a set as the third element, as another element in x. That element turns out to be a set itself with 1, 2, and 3 in it. Okay? So if we are just looking at x, it is a set that only has 3 elements. It's just that one of the 3 elements is a set itself, and then it contains 3 more elements. So remember the analogy of looking at a set as a folder? That works out too, right? Because x is just a folder. In that folder, there are 3 items. A is a file, B is a file, but the next one is a folder itself, which in return has 3 more files. But when people ask how many files are in X, the answer is 3. Okay, so we do not recursively track down the embedded items, nested items. We just say, okay, at the level of X, there are only 3 things in X. So when we are asked the question, is the set 1, 2, and 3 as a set, is that an element of X? The answer is true. But if we are asked whether 1 by itself is an element of X or not, the answer is false. Okay, so 1 is not an element of X. Neither is 2, neither is 3. But the set that contains 1, 2, and 3 is an element of X. Is that okay? Is everybody clear on that concept? All right. So let's move on to section 5. So section 5 talks about, but what if we are dealing with a set that has an infinite number of elements? Because this representation here is really kind of cool. I mean, it's really easy to read. But what if we have an infinite number of elements? For instance, if we want to display, or if we want to describe, no, A and B are not sets. A is just an element, B is just an element. They are not sets because they're not enclosed by curly braces. If it is a set, it is going to be enclosed by curly braces. That was something that we talked about all the way up here. All right. So back to section 5. Oh, okay, we got another question coming. I'm gonna wait a little bit. No, X is itself is a set. Okay, so let me just repeat what I'm seeing in the tablet. So let me turn on the tablet again. Okay, so if we use this notation, X itself is a set. It has 1 as an element, it has 2 as an element. If we say that X is a set that contains an element which is also a set with 1 and 2 inside that particular set, then 1 is not in X, 2 is not in X, but the set of 1 and 2 is in X. Okay, so in the first case, 1 is an element of X is true, 2 is an element in X is true. The set of 1 and 2 as an element in X is false. In the second case, 1 is in X is false. 2 is in X is false. But the set of 1, 2 in X is true. Alright? So we are not drilling down. If we are asking is something in a particular set, then we are only looking at the top level of that set. So we do not automatically recursively look into the hierarchy of sets if there's a hierarchy. Okay, so we got one more question coming, and I'm just swiping to a new page, preparing for more material. Alright, so I'm not seeing any question. There was some typing before, but that's alright. So let's move on. So we are moving on to certain sets that has an infinite number of elements. Oh, okay, there we go. Can a set store different types of elements? Yes. I believe that was discussed earlier, like last Wednesday. There's no limitation of type when we are using a set. So a set can contain whatever you want. I think that was discussed last Wednesday because I specifically used this as an example where we have integers, positive, negative, and also real numbers or rational numbers at least. All right. So I'm going to say this, okay? Don't take it, as a negative thing, but it is kind of important to review the material. In other words, things from previous lectures really should be understood, and we should have knowledge of things that has been discussed already when we move on to a new class, because otherwise we are not going to go very far in this class. Alright, so getting to section 5 again. So how do we represent a set of all even numbers, positive and negative? So one way is kind of like this. It's intuitively expressing what we want to express. So we say E equals to open curly brace. Okay, remember the curly braces are very important. It indicates that we are listing elements inside a particular set. Okay, without the curly braces, it is not a set. So then we use the dot 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 ellipses to say there's something before this, and then I'm just showing a few of the values that are also in this set E, -4, -2, 0, 2, 4, and so on. Okay, but there's no guarantee of what is before the -4. There's no guarantee of what is after the 4. So this is not a very precise way of describing that we have a set of even numbers. So then what do we do? Well, as it turns out, there's a way to do it. Okay, so this is the method, this is the notation. So for the most part, this class has, okay, thank you. I keep forgetting to switch on and off the tablet, especially for forgetting to turn off. So we are now at this point here. Okay, so the mouse cursor is indicating the expression that we want to analyze. So this is how we can express we are talking about a set of all even integers. Okay, so we want to find out exactly how do we interpret this. We have the set notation, the curly braces. So we have the curly brace begin here and it ends here. Okay, so whatever is in between is describing what things are in the set E. Okay, but then how do we read this stuff here? So this X here is declaring what an element is going to look like. Okay, so this X here is just saying each element it looks like just that. Okay, so there's nothing too interesting here. The vertical bar can also be read as such as. Okay, so X such that the following is true. So what is after on the right hand side of the vertical bar is a Boolean expression. So this Boolean expression is telling us what has to be true in order for something to be an element in E. So this restriction tells us that X is an element of this funky looking Z. That funky looking Z is the set of all integers. Okay, so X has to be an element of all, the set of all integers, which is a really long and clumsy way of saying X is an integer. Okay, so and then this little symbol here. Okay, here's your quick quiz that has no points associated. What is this little thing meaning? What is this inverted V indicating here? What operator are we talking about? Conjunction, very good, which is also a fancy name of and. Excellent. Okay, very good. So if you can answer this question, now whether you type the answer in Discord or not is not the important part here. If you can answer this question in your head, that's good. Okay, that means you have somehow retained what we talked about last Wednesday. On the other hand, if you cannot answer this question, now I'm not saying that people who did not type an answer in Discord cannot answer the question. That is not what I'm saying at all. But if you honestly cannot answer this question and go like, I have no idea what this inverted V is about, then you need to study more. Okay, I hate to nag, but this is what it takes in order to succeed in this class. Okay, you got to clear, make sure that you get all the material from a previous class in order to move on. So this is AND. So we need x to be an integer, but we also need this to be true. X mod 2 equals to 0. And exactly what is x mod 2? Is there another way to describe x mod 2? Now this we haven't really talked about, but I am assuming that you know this already because CISP440 is a prerequisite of this class. So yep, okay, so Jonathan has gotten it right. Jack has gotten it right. X mod 2 is the remainder of x divided by 2. So if you divide a number by 2 and the remainder turns out to be 0, that means the number or the dividend is an even number. Okay, so when these two are true at the same time, then we know x is an even integer. Now you can probably argue and say we don't really need x is an integer to begin with, because if x is not an integer, okay, if x is let's say 2.5, okay, 2.5 mod 2 is not 0, and therefore it won't meet the requirement here. Sort of, okay, so it depends on how you define the mod operator in this case, but it doesn't hurt, okay, it really does not hurt to say that x has to be an integer to begin with, and we also want x mod 2 to be 0. So it doesn't hurt to make x being an integer as one of the requirements. Alright, so x percent 2 is the same as x mod 2? Yes. When is mod instead of percent? When a programming language does not recognize percent? Yes, pseudo, that is a good way to put it. Okay, in math papers, okay, in mathematical equations, if you ask your math professors, they do not know that the percent symbol means mod, okay, but they do know that mod mod is means modulus, okay, which is the remainder of a division. So percent is a very specialized symbol that only programmers know, and then the mod operator, mod spelled out, is actually a more common understanding of the modulus operation. All right, so yes, so mod is the same as percent in C or C++. Yes. All right, so in general, okay, so in general we use p of x as a general predicate on x. That basically when we say something is a predicate, okay, that means it is a function that returns a boolean. So when we say p of x is a predicate, that means p is some kind of function, and when I say function in this case, it really is the same function as in C and C++. So it's a function, some kind of function that returns a boolean. Either it returns a true or a false. Okay. So when we use the notation x such that p of x is true, that really means exactly the same thing as what we have here. X is an element of E if and only if p of x is true. So that is not the same thing as only having the arrow pointing one way. Okay, having the arrow pointing two way means that if I find a value and it is not in x, that means p of x must be false. If I do find something in E, that means that something has to make p as a predicate true. But the reverse is true as well. Okay, if I find some x value such that p of x is true, I must be able to find it in E. On the other hand, if I can find some value x such that p of x is false, then I should not find that in E. So the symbol of if and only if is very, very essential in this case. So now we move on and we generalize this. This is a bad word here. It's supposed to be generalize, not just general. So let us generalize this to the following example. X equals to E such that P of E is true. So in this notation, blah, 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 blah. So it's basically saying exactly the same thing as what we had been saying before, which is basically saying this is just a notation. Do we have any questions up to this point about how we describe a set that has an infinite number of elements? Okay. No questions? All right. So if there are no questions, we move on to section 6. Section 6 is something that we have already encountered, the empty set. So a set that has no elements is called, guess what? The empty set. So in this class, we use open and close curly brace as the symbol for an empty set. In mathematical textbooks, they also have alternative representations, but in this class, we only use open and close curly brace with nothing inside to represent the empty set. And I think that makes sense, right? I mean, it's really intuitive to look at this particular symbol here and see it as an empty set. All right, so all the way up to here, all the way up to section 6, we're only talking about, how do we describe a set, okay? The notations of how do we describe a set. How do we know what is in a set, okay? Starting with section 7, we talk about operators, okay? And some of these operators will take on values that are also a set, okay, on each side of the operator. So we'll start with the intersection operator, okay? So this is A intersecting with B. A is a set, B is also a set. So the first thing we notice is the result of this operator is a set as well, because we can see the curly braces. And we can see how we are applying the notation that we were using earlier before. And basically this is saying, everything in A intersecting with B is an element E such that E is in A and E is in B. So this is a very mathematical way of saying the intersection of A and B is a set, where each element in that particular set can be found in A and also in B. All right, so do we have any questions about how we define A intersecting with B? Can I repeat that one? I just used English. And not that I'm trying to be mean, but I really cannot remember what I just said most of the time. So, my words in conversation are extremely transient if they are not planned. You might want to just kind of jot down the timeline, the time mark, which is 12:49, and just kind of go back to that segment in the recording, because I really do not remember what I said. I remember the idea, okay? So I can try it again. A intersecting with B has a result. The result is a set itself. Every element in that particular set can be found in A and also found in B. I think that's sort of what I said, but not exactly. All right, so we got one question. Does that mean A equals B? No, not at all. So now would be a good time to show some examples. But it is also good to see the alternative way of defining A intersecting with B, which is this one here. E is an element in A intersecting with B if and only if E is in A and E is in B. So that's kind of the alternative way of looking at this. All right, so examples. So I'm going to turn on the tablet, and I'm probably going to forget to turn it off again, but you guys can remind me when I do that. So we'll go ahead and look at A, B, C intersecting with 1, 2, and 3. Okay, we'll take a look at this one. So what do we know about the intersection between these two sets? Well, the intersection has to be a set of elements that can be found in both, right? And you look at these two and go like, "Tack, isn't this a trick question? Because one has A, B, C, and the other one has 1, 2, 3. I do not see anything in common between those two." And the answer is yes, you're right. Okay, there's nothing in common between these two. So what do? We say the intersection is empty. There's There's nothing. There's nothing in common. Okay, if you want to use a colloquial word to describe intersection, it is in common. Okay, so let's look at another example. Okay, we got A, B, C, and then the other one has C, B, and that's it. Okay, so you look at these two, you go like, I can see that A is only found on the left hand side, but B can be found in both, and so can C. So now the intersection is a set where B and C are elements in that set. Alright, let's go for some more examples. Okay, let's go for A, B, C in this case, and we are intersecting with B, C, and D. Okay, so this one is just a very slight variation of the one above it. So we look at these two and go like, okay, you'll remember intersection is in common. Okay, so we look at this and go like, I can see A is found only on the left hand side, so A cannot be in the intersection. B is found in both, okay, so B is here. C is also found in both, but D is only found on the right hand side, so C is not in the intersection. So this also only has BC in it. Alright, so I think these are fairly obvious examples. So let's try something that is not so obvious. So now we look at this and say we got AB in a set, okay, intersecting with AB by themselves in a set. And what do you think is the intersection in this case? Now remember, the intersection is a set in which each element can be found in both sets. Yep, alright, you guys are getting this. It is indeed the empty set, because the set containing A and B is not A, the set containing A and B is not B. So there's really nothing in common between the left hand side and the right hand side in this last example. Good job. Oh, okay, one more tricky case and then we move on. Okay, what about this one? Okay, we got A, B, C again, and then we have the empty set here. What do you think is the intersection here? Good job. Wow, that was quick. Alright, it is indeed the empty set, because there's no element that can be found between a set of something and the empty set, because the empty set has nothing in it. Alright? Alright, so I think we're getting the hang of this. So now we move on to union. So the next portion talks about union, and this particular definition here is saying A union with B is a set. Oh, right. Yep, I knew I would forget that. And I did. Okay. And there we go. So now we are talking about union. So if you compare the definition of union versus intersection, it's really similar except for one thing. Alright, so we got Angel asking, how does code handle when sets and elements have the same alias? Not sure, but in this case, Y cannot have XX in it because remember, you cannot have duplicate items in a set. Yep, exactly. So Tom is correct, because in the previous class we mentioned that every element in a set needs to be unique. You cannot have two occurrences of the same item in a set. So Y having X and X in it is not possible. At least not in the context of this class. I believe there's a concept called a multi-set where elements can repeat itself, but the ordering is not important. Well, if they're X, then they are the same, right? I mean, you cannot use the notation X to represent different things in the same context. Alright. Shall we move on? All right, cool. Okay. All right, so we are moving on to union. So A union B, or the union of A and B, is defined to be a set. Okay, we see the curly braces where each element E in that particular set is meeting this requirement. E has to be found in A, or E can be found in B. So the easier way to describe it is everything in the union between two sets can be found in at least one of the two. Okay, so now we can go to the examples. Okay, and reverse. Okay, change all the intersection to unions. So in the first example, we have A, B, C union with 1, 2, 3. Okay, so the union is a much bigger set in this case because it has everything from either. Well, from at least one of them. Okay, but the union cannot have anything extra. Okay, so the union can only contain elements that can be found in at least one of the set on the right or on the left hand side of the operator. In the second example, okay, we have ABC union with CB in this case. So the union is really just A, B, and C. Because, even though B and C can be found in both, they can only appear once in a set. And that's why, it is just ABC in the second example. In the third example, we got ABC in one set, and then we got BCD in the other set. So when we look at the union, it is A, B, C, D. And then when we look at the next example, this one looks a little bit confusing because we have one element which is a set with AB in it, and then we have an element of A, and then we have an element of B. That would be the union between those two. So let me just kind of write down. This is the union of this set and this particular set here. And then in the last example, okay, we have A, B, C union with the empty set, and any set unioned with the empty set is itself. It's just kind of like adding 0 in arithmetic. Okay, x plus 0 is just x. So anything union with the empty set is the original set. Okay, the set that we just mentioned is a set. All right. So are we good so far? Looks like we are not getting questions at this point. Then we're going to move on to what looks like a subtraction, but it's not really a subtraction. Okay, sort of, but not exactly. So A minus B is called the difference. Okay, you can say it's the difference between two sets. So let's look at the definition. So it is a set itself because we see the curly braces, and the description of the set is E such that E is in A and E is not in B. So this is where, instead of using the word and, the word however or the word but is better because it is contrasting. Yep, again. Okay, I need to find a systematic way to fix this. Okay, maybe I will find a different way to shrink the tablet screen so that, well, I don't use the lines too much. Let me see if you guys find this acceptable or not. Just give me a moment to resize the screen and then put it on top of the browser. If you guys think this is fine, we'll use it this way because this way I won't forget. Alright. Is that okay? Because you can see some lines are sort of faint and some are disappearing completely. Is that okay? Yeah, okay. Alright. So we'll do it this way then. Because this way, I won't forget because this is exactly what I'm seeing too. Okay, cool. So we'll go ahead and do it this way. I just knocked my mic out of the way. Alright, so where were we? Subtraction, that's it. Okay, so subtraction is something that is found on the left hand side but not on the right hand side. So we're excluding things that are from the right hand side but is on the left hand side. So we'll go ahead and use the example that we have already shown here. So we have a, b, c minus 1, 2, and 3. We know the result of a difference is also a set. But what is in that set? Everything on the left hand side but not in the right hand side, right? So in this case, it would just be A, B, and C. Because these three elements can be found on the left hand side, but they cannot be found on the right hand side. Alright, so let's work out the second example. We got A, B, C minus C, B. Okay. So this time we only have A in it, because only element A is found on the left hand side but not on the right hand side. C and B are also found on the right hand side, and so when you look at the difference, element C and element B do not belong to the difference. Okay, so we got one question coming on the text channel. Alright, so because 1 is not in ABC, 2 is not in ABC, and 3 is also not in ABC, so they do not get removed in the result. Okay, very good. Now we move on to the third example. Okay, so we got A, B, C minus B, C, D. And the answer is just A. Then what about the D? Well, D doesn't really matter because D is not even found on the left hand side to begin with. So nothing that does not appear on the left hand side can ever be in the difference. In other words, when we look at the difference, it can only contain elements that is on the left hand side, but we have to get rid of things that are also on the right hand side. I'm not really sure about appending. What do you mean by appending? Because remember, in a set, ordering is not important. Appending usually means that you are adding things to the end of a list. There's no such operator. There's no plus operator between two sets. If I were a compiler, I would say operator not defined for the set for the type. Alright, so let's work out two more examples and then we'll move on to the next operator. So we have the set of a set of AB minus the set with just A, B in it. So in this case, it will be the set with AB in it. No, plus is not the same as union. I'll just say it plain and simple. There's no plus as a set operator. You might think that it has some similarity between union and addition, but there's no addition operator defined for sets. Okay, we got a few more people typing. Okay. An array is not a set is not an array. That's something that we talked about on last Wednesday, because in an array, items are order dependent. In a set, there's no inherent ordering between items. Alright, so we got two more people typing in the text channel, so I'm gonna wait a little bit. Well, okay, so to address Aiden's point, it depends on the notation, because in most scripting languages, the use of square bracket indicates it is either considered a list or an array. Okay, so for our discussion, they are really the same thing because they both have ordering, built into it. So, when we use two lists and then we use the plus operator, I believe most scripting languages will do the appending, which means the result is 1, 2, 2, 3 as one longer list. Yeah. So when we append those two, it would become 1, 2, 2, 3. 2 would appear twice because we do not eliminate duplicate items when we are dealing with a list or an array. And that's why it is important to understand that a set is not an array. A set is not a list either. All right. Okay, so one more example to go through. We got A, B, C in a set minus the empty set. This one is easy. The empty set has nothing in it, so we cannot exclude anything from the result. All right. So now we move on. And we move on to something that looks like a multiplication, but it is not a multiplication. Okay, so sometimes we borrow operators that that we use from arithmetics, but it's not the same thing. Okay, so when we look at A, this is called the Cartesian product. Okay, so when we look at the Cartesian product of A and B being two different sets, then the result looks like this. So this is the one time, okay, at least the first time, where we see the use of something other than just a simple symbol, before the bar, before the such that. So in this case, when we look at the Cartesian product between A, B, each element in the resulting set, I should say. So every element in the resulting set is what we call a two tuple. Okay, so x, y, is a two tuple. And in the two tuple x, y, x is an element of A and y is an element of B. All right. So this one, I think the best way to illustrate this one is an example. So let's go ahead and open a new page and look at some examples here. So we'll start with something simple. Okay, we got A, B, Cartesian product with 1, 2. So the end result is a set to begin with, and then every element in this set is a two tuple. A tuple is basically kind of like a container, and this time you can say, oh, but is that a list? Is it an array? Yes. Okay, a tuple is basically the same idea as a list or an array. So ordering is important, and the same value can appear multiple times. So when we use the term two and then a dash and then a tuple, all that means is an array of two items. That's basically all that means. So in this case, we end up with a two tuple A1, a two tuple A2, a two tuple B1, and a two tuple B2. It has 4 elements. So the result of AB Cartesian product with 1, 2 has 4 elements. So, okay, this time I did exactly the opposite, which is forgetting to pop the tablet onto the screen, because my tablet is actually a physical device, so I can write on it, but then I forgot to put it on the screen. So let's look at this example and see if you guys have any questions before we move on to another example. Okay, we got some questions coming. That's good. That means you guys are paying attention. All right. Scroll. Oh, right. Okay. All right. So let me pull this down a little bit. There we go. That's good. There we go. Alright, so are there any examples? I mean, are there any questions? It's sort of like FOIL, yes. Okay, so if there are no questions about this one, let's look at another one. Okay, so this time we have A, B, C as one set, Cartesian product with just one, the set of just one. Then the answer is it has three elements. It has got A1, B1, and C1. Okay, so the second example is, I would say, pretty straightforward when you compare that to the first one. Okay, any questions? Okay, someone posted something in the general text channel. I'm gonna take a quick peek at it. Okay, so Andre, you need to use the text channel of today's date. The general channel is not used for class or lecture specific discussions. All right. If there are no questions about this, we'll move on to the next one. Okay, so we have AB as a set, Cartesian product with AB as a set. Okay, so this time we have a Cartesian product of a set with itself. Okay, so now we got AA. Okay, poor penmanship here. AA. We got AB. We got BA. And then we got BB. So this one clearly illustrates that in a two-tuple, you can have duplicate items. And ordering is important, because otherwise AB and BA would not be considered two separate elements. So I'm just going to let you guys finish asking the questions, and then we'll see whether we need another example. What type is A1? A1 is a two-tuple. It's a tuple, which means it is an array or a list, and it's a two-tuple because it has two items in it. Either one is fine. Ordering is important, and you can have duplicate values in it. So you can look at it as an array, or you can look at it as a list. The idea is, the ordering is important, and you can have duplicate values at different positions, or you can have the same value at different positions. And now would be a good time to take row 2. Okay, so I'm keeping an eye on the text channel, but I'm also going to set up the row taking thing in Canvas. Alright, so we are talking about set theory, so I'm going to put it under set theory basic, and it's going to be similar to the last time we had an activity like that. It will look like a quiz, but it's not. Okay, so this is for row taking. Okay, cannot remember the format that I used. Row taking. Okay, so I just want to be consistent, and this is row taking, and then today's date is 0125, and we'll put it into the row taking category, which means it basically does not count for any points for your grade at the end of the semester. I'll address the last question after we get this done, okay, because this is kind of important. And we'll go to edit. Right, restrictions. So I will restrict it to, I'll give you guys a little bit of time to do it. I'll give you guys up to 1:30 p.m. to get this done. It will take you like, a minute to get it done. So, that should be fine. And I have to add a question to it. And since you're looking at me, creating the question, the answer would be pretty clear. Okay? And this is going to be a fill in the blank kind of question. What word did tag use for row taking purposes? For today, of course. And then the answer is tuple. Tuple is the word. Okay, but don't click yet because you won't be, it's not visible to you yet. So let me update question, save and publish. There we go. So you should be able to see it now. I'll give you guys the time to take roll first, and then I'll go answer Angel's question. Okay, so click on row taking 2021-0125, which is under set theory, and then the word is tuple, T-U-P-L-E. That's right. All right, cool. So I'm getting back to answer Angel's question. We can have a set with arrays as elements in it. That is correct. Okay, so a set can have an array, and in programming we can also have an array where each item is a set. Okay, those concepts are orthogonal. They are not dependent on each other. Okay, so let's see, yeah, we got 2 more minutes left. So we have a few more examples to go through in the tablet. So I'm gonna switch back to the tablet now. Okay. So if you have any trouble, getting through the row taking activity, let me know. And you guys can do this up to 1:30. So you have another more than 20 minutes to do. 10 minutes, more than 10 minutes to do it. So that's quite a bit of time. All right. So I'll give you a few more examples. So we have the set of AB, and this time we are doing a Cartesian product with the empty set. So now the question is, what is that going to be? Now remember, everything in the Cartesian product between 2 sets needs to be a 2-tuple, where the first item of the 2-tuple comes from the left-hand side of the operator, and then the second item comes from the right-hand side of the operator. Okay? But when you look at this particular example, where we have AB as one set to the left-hand side of the operator, but the empty set to the right of the operator. So the answer is, it is an empty set, because there's nothing you can get out of the set on the right-hand side. So there's no way you can actually create a 2-tuple to put into the set representing the result of the Cartesian product. Okay, so let's look at it the other way. Okay, so if you look at the Cartesian product thing, if I were to code it, okay, it would be a double loop, right? So let's just say, now this is completely pseudocode, but I'm going to use the concept of pseudocode. So this is the return type. It is a set, and this is called the Cartesian product. Okay. And the parameters would be A, which is a set, and B, which is also a set. Okay, so I'm using pseudo C code here. Alright. Why can't it make an array with single elements? Because that is not how it works. Because a Cartesian product needs to create 2 tuples. The first item coming from the left-hand side, or A in the function, and then the second item coming from B. So when I code this in pseudo C mode, okay, this is how I would put it. Okay, so the set representing the result is initialized to the empty set. Okay, and then what I do is I say for each element lowercase a in A, and then for each element B in B. Okay, so lowercase is the element, uppercase is the actual set, which is the parameter. So if I ever get to this nested portion here, I would say add, okay, in parentheses AB to result. So result is a local variable, so that I can keep track of what I need to return to the caller. So I'm doing this kind of in C mode, so I should probably use a bunch of curly braces for that. So we have curly brace, and then close this curly brace. Alright, so the question now is, if A or B is empty, then we cannot get to this point here. Okay, we can only get to this point if there's at least one thing in A and there's at least one thing in B. Then we can get to the add AB to result line. If A is empty, we won't even get to for each B in B. If B is empty, we still cannot get to this point here, which means if A or B is an empty set, then the Cartesian product is also going to be an empty set. Now I know I'm running out of time, so I just want to finish this pseudocode here. Return result, and that's kind of the pseudocode of Cartesian product. Alright, so we are out of time today, and I do want to point out what I would like you guys to do before Wednesday. So we are going to be able to finish the entire module for sure, because we are already kind of really close to the end for this module, for this particular link. So on Wednesday, we'll be talking about quantifiers, and maybe I think there's a good likelihood that we can also move on to set theory using quantifiers. So I would like you guys to read ahead of the class. Okay, first of all, make sure everything that we have talked about so far, you understand all of that stuff. And then we also want to be able to read a little bit ahead of me, ahead of the class, starting with quantifiers and then moving on to set theory using quantifiers. So that's kind of what I would like you guys to do before Wednesday. And then by the time we're done with Wednesday, we'll have our first official homework assignment, that will kind of ask you some questions about set notations. So that's the end of today's lecture. I will stay online for maybe a few more minutes, just in case there are questions about the content of today's class. Other than that, I am going to disconnect from screen share and also from voice chat, and also disconnect from the YouTube stream. But I will stay online for I'll stay online until like 1:30. How about that? So if you have questions to ask, you can use the text channel, or you can just call me using a direct message on Discord. So all of those methods will work. All right, I'll see most of you on Wednesday then.